Lesson number 3.
Yeah, today we're looking at geometric distributions. Just a quick recap. Lesson 1 was uniform distributions, where each outcome is the same probability, 1 out of 6, 1 out of 6, 1 out of 6. We looked at binomial distributions last lesson, where you have success and failure are your only options. You have a certain number of trials, and the probabilities are independent. Geometric distributions will sort of take some of what you already know about binomial distributions, and we're going to apply it to a slightly different context.
Yeah, it's like we're going to use a binomial distribution, but we're going to ask a slightly different question.
Yeah, so like if we were to ask, A, what's the probability of this or this? B, what's the expectation or what's the expected value? This could be a C, right? What we're going to show you what to do today. So like binomial distributions, geometric distributions have only two outcomes, success or failure. We're going to call them P and Q, just like we did before. They don't change from one trial to the next, so they're independent. However, the random variable for geometric distribution isn't the number of successes. You know how we had P of 0 would be the probability of no successes. P of 5 would be the probability of 5 successes. Here, when we do P of 3, they're saying what's the probability of 3 unsuccessful trials before you get success on the fourth. So this is, it's a little bit different. It's all about waiting time. How long do you have to wait
until you see
success? If you go to IKEA, they've got this machine that pushes on one of their chairs to see how many pushes, how many times can you rock that chair before it breaks. And so that's sort of a geometric distribution. If we can calculate what's the waiting time, what's the number of unsuccessful trials, what's the number of times we can move it before we finally get that last thing we're waiting for, which was for it to break.
So a couple examples, basically the IKEA example fits in beautifully with part B down here. Also in Monopoly, if you go to jail, you're given the option, you can kind of pay a certain amount of money to get out of jail, or you can try and roll doubles and you can get out of jail for free. So basically in a board game, if you can't get out of jail until you roll doubles. So basically what's the probability
wait time
that you're going to have to wait, or what's the expected waiting time before you'll roll doubles on a dice? So these are the types of things that we can model with a geometric distribution. So it has the same properties as binomial distribution. Everything we've kind of talked about before. We're just asking a slightly different question.
Now here's what's neat too, and notice the last line on this slide, is that order matters for geometric distributions. Because we're waiting success. You know, in order to have success on the last one, you have to actually fail for all the first ones. So we don't put that n choose x at the beginning, because it wouldn't be geometric if we failed, succeeded, then failed. Well, you know, there wasn't a wait time for that, right? So you'll notice that it's got a similar feel, but because order matters, we don't use combinations at the beginning.
No. Okay. So let's take a look at probability in a geometric distribution. And again, this is the probability of success after waiting a certain amount of failures before we get that success. So here it is. The probability of this number of failures is equal to the individual probability of failure to the power of x times p.
And picture this. If you were to have 5 trials and you wanted to know the probability that you'd have to wait 4 trials before achieving success, you'd find the probability of 4 as your wait time, and then notice your q to the x. That would be fail, succeed. And notice the order. Because we're waiting for that final thing to happen, that probability of success is the last thing. And it's like there's a series of stages that you're making choices at, and these are lined up in order. So we're going to fail, succeed.
So let's think about maybe what this geometric probability distribution might look like. Let's say if we're flipping a coin. So there's going to be some probability of success, some probability of failure. Let's say we say that heads is success, and we're waiting to flip a heads. There is a probability that we could get it right away. So no failures, we flip a head right away.
So no wait time.
No wait time
P
at
of
all.
0.
P of 0. Then we could say, okay, well, let's say that we could flip basically a tail before we get heads.
So we fail once before succeeding.
Then we fail twice before succeeding. Then we fail 3 times before succeeding.
Well, it's possible, Mr. Jackson, you could fail like 100 times before succeeding on the 101st.
It's also possible However be it, it's a small probability, but there is a possibility that I could fail 1 billion times.
You could spend their whole life rolling tails.
Exactly.
And never get heads.
And I know, and that's exactly it. So basically, we can talk about finding the probabilities of all values from 0, basically no waiting time at all, to an infinite number of failures before we see success.
Oh, and that's because they haven't given you a number of trials. They haven't given you n equals 8 or anything like that.
Now, although an infinite number of failures before success is possible, and is theoretical, it's impossible then for us to construct
a full distribution,
geometric distribution.
Yeah.
Because basically the probabilities begin to converge on 0, because of course if you're flipping heads and tails, the probability that you would flip 1 million tails before you would see a head
on the million and
is basically 0. Like the probability is so tiny. Even the probability that you flip 50 heads before, or 50 tails before you see a head,
is still almost 0.
Yeah.
You can liken this, if you've taken advanced functions, the limit, as x approaches infinity for the number of failures before success, the limit as x approaches infinity for this probability distribution is 0. Right? So you can picture that it's a curve that's reaching towards that x-axis, reaching towards the 0 line.
Okay. So here's an example. To make your first move in a board game, you must roll a 6 on a standard dice. What's the probability that you get a 6 on your first roll?
Oh, okay. So I want 6.
Yeah.
Okay, I'm waiting for a 6. Go 6. So 6 is a success. Yeah. I know there's a 1/6 probability of rolling a 6. So then everything else is failure. Everything that's not 6 is not a success. So that's 5 out of 6. If I want to get it on my first roll, then that means I haven't had any failures first. So I'm looking for the probability of 0. There it is. Probability of 0 failures. So I'm going to do q to the 0 times p. Right? All right. So q to the 0 is 5, 6. So I don't have any failures. Boom. And I get my success rate on the first try. Okay. And that's what you'd expect.
Basically is what you'd expect.
You just could do it
simply like sailing. It's basically, what's the probability that you get a 6 on your first roll? Well, it's 1 in 6.
It's 1 in 6. Yeah.
Right?
Yeah.
What's the probability that you get a 6 on your 4th roll? So basically, you failed. Now everyone's in front of you, and
then you got 6.
Then you get your 6.
So this is trick. You're not finding p of 4.
No.
Because the x here, the random variable is how many failures before you see success. You got it.
So here x is equal to 3. So P3, 5 over 6 to the power of 3 times the probability of success.
Yep, so fail, succeed.
Yeah. And that's 125 over 1296. So on your 4th roll, the probability of seeing success is about 9.6%.
Yeah, that you have to wait 3 times before you get success.
So now let's actually make this even more complete. We say, what's the probability that you get a 6 within your first 3 rolls?
Okay.
And we would hope that would be a relatively large probability.
Yeah.
Right?
Yeah, so you roll it once and you get it right away, so no failures. You roll it twice and you fail once before you succeed. Yeah. Or you roll it 3 times. You're going to get it on the 3rd, so you've failed twice before succeeding. So this, again, just takes a little bit of planning and thinking. What does within 3 rolls mean in terms of our discrete random variable, or the number of failures, and that's going to be 0, 1, and 2.
So when we actually figured this out, here's P1.
Yep. We've already done probability of 0. That's 1/6.
Here's P2.
Okay. 25 out of 216.
So let's add them up.
We add them up. You can make some common denominators. You can use your calculator.
And we get 91 out of 216.
Yeah.
So it's about a 42% chance.
But within 3 rolls, you'll get that 6 you need.
We get asked tons of different questions. Hey, what's the probability that you get a 6 within 6 rolls?
Yeah.
What's the probability you get 6 within 10 rolls? Of course, all of those probabilities start to build up and closer and closer and closer.
Yeah.
So the expected value, though, for a geometric distribution is also very useful, because it's telling you the expected number of failures before you'll see success.
But, the expected value is just, the random variable times the probability of getting that value plus the next one. But there's an infinite number of discrete random variables that you could have, like an infinite number of failures before success. So what's neat about this is that to calculate the expected value, or E of your X, your random variable, it it converges. Okay, so again, if you're talking about limits, right, it converges on this wonderfully simple formula. So you don't have to calculate an infinite number and then average it, thank goodness, that the expected wait time is given just by the probability of failure divided by the probability of success. So, whatever you're waiting for, that its probability is in the denominator. So Q divided by P, and that gives you, that's what it converges on, because you start adding values that are almost zero at the end of that distribution anyway.
All right, so here it is. A basketball player has a success rate of 68% for scoring on free throws. Okay. What is the expected waiting time before the player misses a basket?
Okay. Now this question, the wording on it is a little bit tricky. They're telling us 68% success for scoring. So scoring is a 68% success rate. We're being asked the wait time before he misses. So actually what we're waiting for, we're waiting for a miss. So in fact, the thing we're waiting for is our p-value, because it's q to the x times p. So a miss is that thing we're waiting for, is that thing we're waiting to check off, is it going to be our p-value. So technically a miss, we're going to call it success.
And we see here that until you become very comfortable with the wording and exactly what it is you're looking for, following what we do in an example is useful to kind of introduce it, but really most of the work in figuring out these problems is going to come on your own, interpreting the wording of problems and doing some questions in the textbook, right? Because that's where all of your familiarity is going to come from, saying, oh, what's the expected wait time before the player misses? Oh, I'm actually looking for misses and not successes.
I'm waiting for a miss, not a score.
So here, basically, we have to say, well, what is a success in this case? And what is a failure? Because in this case, what we, as the data managers, are waiting for is basically missing a shot. And so that's what we're going to call a miss, a success. Making a shot then is a failure. Okay? So basically then, according to the formulas for EX and PX, making a shot is defined as a failure.
Because it's the thing we're counting and waiting for.
Okay. So Q then is 0.68. P is 0.32. And if I want the expected number of scores before he misses, or before
before she misses, it doesn't say.
Basically, we get 0.68 divided by 0.32, and we're looking at about 2.1.
So we'd expect on average between 2 and 3, but closer to 2, scores before a miss.
Okay, so here's example 3. Suppose you pass a traffic light on your way to school each day that alternates between being green for 40 seconds and then amber for 60 seconds. Red, I should say amber or red for 60 seconds. So basically you're going to be able to go 40% of the time and you're going to have to stop 60% of the time. Okay. What's the expected number of days you must reach the intersection before you get a green light?
Okay, so now they haven't said in here the word wait or wait time, but when they're saying what is the expected number of days you reach the intersection before you get the green light, they're asking you for that wait time.
How many times are you going to be waiting there?
This is how we know it's geometric. And so if we want the expected number of days that we have to reach it before we're going to achieve success, we're going to determine that if we're waiting for the green light, then the green light is going to be our p-value. It's our probability of success. That'll be 0.4. And then our q values are 0.6, is everything that's not green. And then we just want to figure out, okay, well, the expected number is the expected value. And we know for geometric, it's just q divided by p. So we do our 0.6 divided by 0.4. That gets us 1.5. Now, this is where we have to be careful because, 1.5, is it that, between 1 and 2 days, then you get a green light, or how do we interpret this? So since we're being asked the expected number of days we must reach the intersection before we get the green light, then our answer is, well, then we'd have to wait 1 or 2 days before getting a green, which means that we wouldn't get the green until the 2nd or 3rd day. So you either wait 1 day and get green on day 2, or you'd wait 2 days and get green on day 3. So that 1.5 is between 1 and 2. And that way we can reword it for a layperson who doesn't know what expectation or expected values are.